Hello. My name is Mengu from Kyushu Institute of Technology, Japan. In this presentation, I'd like to talk about the CubeSat interface standard draft. First, I ask you a question. Are CubeSats delivered fast? It has been said that the advantage of CubeSats is low cost and fast delivery. Low cost is probably true. Some can build a CubeSat with $30,000 or less if it is designed carefully and manufactured with good hands. But are we making CubeSats fast? The answer is not really. Many projects are still taking 2 years or longer from the project kickoff to the launch. In December 2019, we had International Workshop on Lean Satellite at Tokyo to discuss various issues related to Lean Satellite, which is almost equivalent to small satellite and includes CubeSat as well. During the workshop, I asked a question about how to improve the CubeSat delivery time to CubeSat developers and vendors. Many people listed interface. It is also interesting to see software interface and integration are listed by many. We now look at the effects of interface incompatibility. It does not affect the satellite reliability directly, because the interface incompatibility should have been solved during the system integration before launch. In principle, not many issues should remain unsolved when the satellite is launched. But the interface incompatibility leads to delay in the schedule, because we need more time to solve the interface incompatibility issue. We do many try and errors during integration and testing phase. Then, there will be less time to spend in other verification processes, such as deployment, software, communication, thermal, others. Then the mission success rate will decrease. Also, the delivery time gets longer. This is result of another survey done in the last Lean Satellite workshop. About 1/3 of the CubeSat vendor bought component from single vendors. The reason why the developer chose the single vendor solution or multiple vendors solution are listed here. The requirement on performance and functionality dictates and make them to buy from multiple vendors. 3 chose the single vendor solution to avoid the interface incompatibility. Nowadays, more CubeSat developers prefer the single vendor solution to avoid interface issues. Some are not interested in making a satellite. They just want to demonstrate their ideas or payload only. To adapt to that trend, many CubeSat vendors are moving to offer so-called CubeSat platform. It is a combination of CubeSat bus components having empty slots for mission payload. Everything other than mission payload is already prepared. This summer we searched internet to check how many companies offer this CubeSat platform. Amazingly, we found 27 companies worldwide. There are even a company who offers hosted payload service based on CubeSat platform. For the hosted payload, the customer just brings the mission payload to the service provider. The customer does not have to own the satellite. They can share a satellite with other customers, lowering the total cost of doing space mission. It is good for quick technology demonstration if it really works out. We found 6 companies worldwide offering this hosted payload service. This is the list of platform providers. It covers from 1U to 12U. We tried to find interface control document in the company's URL. Only few companies offer ICD, but the information available is not enough for most of the cases. This is the list of companies offering hosted payload service. Only one company, German Orbital Systems, provide ICD in the public domain. I hope other companies offer ICD upon request of quotation or something. Also, when we consider interface of CubeSat, we should think about the mass production. Now, small satellites are entering into the era of mass production. It is more true for CubeSats as the unit price, and the launch prices are much cheaper than the other classes of lean satellites. To do mass production, physical interface becomes very important. Satellite assembly, integration, and testing can be done in parallel by making the satellite harness-less, adopting batch production, and batch testing. To do so, the satellite interface must be designed from the beginning to adopt rapid and uniform assembly. This is a picture when my students produced 5 1U CubeSats simultaneously. At each table, 2 or 3 students assembled a satellite. In terms of quality control, it is a nightmare considering the poor hand skill of the students. To make the matter worse, they were all beginners of satellite making. To assure the uniform and good quality as much as possible, this type of harness-less design was adopted from the beginning. To do so, the interface of each PCB components must be designed carefully. By having a standard interface, especially without any harness, the assembly process can be accelerated greatly. During the Lean Satellite workshop, I also asked about the harness. There is still a long way to go to a harness-free CubeSats. The major reason is solar panel, payload bus interface, umbilical, and others. I can understand that to connect with something at the external panel's harness may become necessary. But with careful design, we can remove the harness even from the interface between the external panel and the internal units. So, let me summarize the needs of standard. CubeSat components and platforms are traded worldwide via Internet. We have a standard of CubeSat external shapes, which is the Cal Poly CubeSat standard. It is now an ISO standard. It is numbered as ISO 17770. But regarding interface between internal components and interface between CubeSat bus and mission payload, no standard exists. In the satellite design phase, we want detailed information about product interface for the product selection and configuration design. Often it takes long time to choose the vendor because we cannot have enough information in the public domain. In the satellite assembly phase, good physical interface is needed. In the satellite integration and testing phase, physical and software interface compatibility is critical. The benefits of the CubeSat interface standard are the following. It can shorten the time required for design, development, assembly, integration, and testing. It can promote mass production. It can assure component compatibility, leading to promotion of international trade of CubeSat components and international collaboration. So, the interface is very important for CubeSat. Therefore, I started a new project to standardize the interface in 2019. The project is funded by the Japanese government. Its goal is to make an ISO standard to define interface of CubeSat. My target is to have the standard published in 2024. In the standardization project, we do the following 5 things. Making and revising the standard draft. Coordinating with ISO TC 20SC14. Investigating compatibilities among CubeSat components in the market. Collecting inputs from the worldwide experts and stakeholders through IAA, International Academy of Astronautics. Organizing international workshops to exchange information and to discuss the standard. The project proceeds in parallel with IA Study Group 4.26. I used a similar method when I led the activity to make the testing standards and the requirement standard. There is an official website called LeanSat. In this website, you can access to all the previous meeting minutes, presentation, and others. We have a mailing list to distribute the information. If you want to join, please send me an email to me. Now I talk about what is included in the standard. It contains the following 5 items. Interface among components. Interface between platform or bus and mission payload. Document specification to describe the component interface. Document specification to describe the platform interface. External electrical interface, umbilical. I need to explain why the standard contains the document. It is based on the discussion at the Lean Satellite workshop of last year. I identified proper documentation, datasheet, helps selection of components to buy if common items are listed for comparison. Also, it helps during system integration and testing if technical information is written in detail. For CubeSat products, the communication between the customer and the vendors are limited. We do not have luxury of visiting the vendor directly. The documents associated with the product are often the key, or often only one, item to ensure smooth system integration and testing. Now I introduce you the standard draft. The standard draft is available at the Lean Satellite webpage. To download, you need a password. To get the password, please send an email to the address shown here. This is the table of contents. It is made of 8 chapters and 3 annex. Chapter 5 to 8 are the parts that write the normative requirements. This is the first chapter, the scope. This document describes internal and external interface of CubeSat. The internal interface includes the interface between components and the interface between a CubeSat platform and a mission payload. The document also describes the items to be included in the datasheet of the CubeSat components and platforms. The datasheet requirements apply to catalogued commercial products ready for sale. The interface between CubeSat and its deployer, i.e. Payload, is not included in the scope. For the unit-to-unit interface, I write the one for PC 104 style and the one for backplane style. Please read the draft for the detail. For the backplane style, I wrote an example in Annex C using QTech 1U satellite as an example. For PC 104 style, I put 3 figures. One for physical layout of mounting holes, and 104-pin connectors. Please check the numbers are correct. The maximum envelope size and the locations of connector and mounting holes are defined for mating compatibility. The requirements on the stacking condition are described by using Figure 2. By using this figure, the draft defined the connector pin assignment. I list only 10 pins so that very little change is necessary for the products already in the market. For the backplane style, I write examples in Annex C, where you can find examples of backplane style for 1U and 3U CubeSats. The Annex introduces the PCB size, requirements on the backplane, pin assignment, and others. Chapter 5.2 describes the mission payload to platform interface. For the detail, please read the draft. Chapter 6.1 gives general requirements of items to be listed in product datasheet. There are more items in the standard draft. Please read it. There is an ISO standard, ISO 11892 subsystems units to spacecraft interface control document. The standard is for traditional satellites, which assumes that a component comes in a box and the box is bolted to the satellite panel and electrical connection is made by harness. I tailored the standard to fit to CubeSat. I also listed specific item for each type of unit, such as EPS, communication, ADCS, etc. In the Lean Satellite website, an example provided by a Japanese company who makes UHF radio for CubeSat is available. Chapter 7 gives datasheet requirements for CubeSat platforms. An example made from the Birds platform of QTech is available at the Lean Satellite website. Chapter 8 briefly describes the umbilical. If you have comments to the standard draft, write in the comments sheet. The comment sheet is a standard format used for ISO draft. It is also available at the Lean Satellite website. Please write your name, which part you are referring, and your comments. It is a tabular form in Microsoft Word. Send the comment Word file either to me or the mailing list. The updated version of the standard draft will be discussed in various CubeSat-related conferences, such as Small Satellite Conference, International Astronautical Congress, and others, including the next Lean Satellite Workshop. I'd like to announce the next International Lean Satellite Workshop. In the workshop, we will discuss more about CubeSat interface and also various other issues. The workshop will be at City of Kyushu. You can enjoy nice food, nice scenery, and nice meeting. I hope that it will be a good time to travel by then. Until then, please stay safe.